All right, so we're doing 5.3 exponential functions. Exponential functions, the way I remember it, is we have a base and we have an x in the exponent, and then it qualifies as an exponential function. Okay, so in order to evaluate exponential functions, which is our first learning objective, we got to figure out how our calculator works. Sometimes some calculators, scientific calculators, the smaller ones, will want the exponent first, and sometimes they will want the exponent, put the base in and then the exponent. You guys should all be using a calculator that you put the base in first and then the exponent. But just, make sure whatever calculator you're using, you know how it wants its exponents and bases. All right, so when we evaluate, looks like 2, we use a little caret. It's the caret like in jewelry, not the caret that we eat. So if we're evaluating, we are just finding the approximate value when we raise our base to our exponent. Any questions? There is no writing action item here. Any questions on that? All right, do not forget the laws of exponents. It's easy when it's been a while since we've done exponents. So if I am multiplying 2 of the same bases together, I can write it as one base with the exponents added. If I am raising a base and power to another power, I'm just multiplying the powers together, same base. If I am multiplying 2 bases together and I raise that to an exponent, that's the same as base to that exponent times my other base to that same exponent. You can distribute out the exponent to the parentheses. Cannot do that when there's a plus or minus, but you can do that when there's a multiplier divide. 1 to any power. 1 to any power is 1. If I have a negative exponent, if my base is a whole number, it either creates a fraction, or if I already have a fraction, it flips it, and then the exponent's positive. Anything to the 0 power is 1. All right. Tons of stuff in the real world is modeled using exponential functions, like exponential growth. We have a function that doubles with every 1 unit of increase. So the value of f when x is equal to 0 is 5. So we start with 5 and we're going to double it each time. So we get 5, 10, 20, 40, 80, 160. Back. So when you take your initial value, and then whatever action you're doing, if you're doubling, your base is 2. If you're tripling, your base is 3. If you're quadrupling, your base is 4. And then you raise that action item to the exponent. All right, so an exponential function officially is some constant, which is our initial value, times a base, which they're calling a here, raised to an exponent x. Its domain is all real numbers. The base is the growth factor. F of 0 is c. Hold on, I'm going to escape out of this real quick. For an exponential function, f of x equals c times a to the x, where a is bigger than 0 and a is not 1, if x is any real number, then f of x plus 1 over f of x is equal to a. Or f of x plus 1 is equal to a times f of x. So essentially what this is it's like in Algebra 2 when we had a geometric sequence and we were trying to find the common ratio, where we take the term before the next term and divide it by the term before, and you get that common ratio. Same kind of concept, just now written differently. Okay, so if we are given, and you don't have to write this down. If we're given data, we need to determine whether they're linear, exponential, or neither. Good job, guys. All right. So for our function, for each function, compute the average rate of change of y with respect to x and the ratio of consecutive inputs if the average rate of change is constant. So essentially they're saying, are you adding or subtracting by the same amount each time? If the answer is yes, then it's linear. If you're multiplying or you're changing by a multiple each time, then the function is exponential. So when you look at the first one, you notice that we are decreasing by 3 each time. That means our average rate of change is -3. And if you try to do the 2 divided by 5 is 2/5. -1 divided by 2 is -1/2. -4 divided by -1. So they don't have a ratio that's constant. So this one gets to be linear. And if we're putting together a linear function, the slope is -3. The y-intercept is 2, so this is f of x equals -3x plus 2. The second one does not have a constant average rate of change, but it does have a constant ratio of 1/2. So with a constant ratio of 1/2, our initial value, so when x is equal to 0, our y is equal to 16. So our function is g of x equals 16 times 1/2 to the x power. The third one does not have an average rate of change that's constant, nor does it have a ratio of consecutive outputs that's constant. So it is neither. All right, let's look at the graphs of these guys. When you have an exponential function, if you raise a base to a negative exponent, you do not get a negative number. You just get a very, very tiny fraction. The more negative your number is, the tinier fraction you have. So it will approach 0, but it won't touch it. Let's look at what that looks like. So an exponential function, when you're in the negatives, you're going to be rolling real close to the x-axis, and then it's going to go through 0, 1, because anything to the 0 power, if I raise it to the 0 power, I'm going to get out 1. And then it's going to start growing exponentially, quickly. So if we look at some data of number of cellular phone subscribers at year end, it has a nice little exponential growth to it. So we start out kind of small, and we get bigger, 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 bigger. the bigger the base, the steeper your exponential curve is going to be. You still go through 0, 1, because anything to the 0 power is going to be 1, but the bigger your base is, the steeper your exponent function is. All right, so let's write down these properties of the exponential function. If f of x equals a to the x, where x is greater than 1, the domain is a set of all real numbers, and range is a set of positive real numbers, because even if we put a negative value in, we're only going to get a fraction and not a negative number. There are no x-intercepts, and the y-intercept is 1. The x-axis is a horizontal asymptote as x gets closer to negative infinity. The graph contains the point 0, 1 and 1, a, whatever your base is, and negative 1, 1 over a. So when you do this on the little quiz or the practice, and it's asking you to click points to create the exponential function, make sure you're clicking on 0, 1, 1, whatever your base is, and negative 1, 1 over whatever your base is. The graph is smooth and continuous with no corners or gaps. All right, so if we're going to graph an exponential function, so we're going to take a look at f of x equals 1/2 to the x power. When I plug in, so now we have a situation where our base is less than 1, but bigger than 0. So in this instance, if you look at, if I raise this to the negative 10 power, I'm at a giant number. If I raise it to the negative 3 power, I'm going to get a medium number. Raise it to the negative 2, I get 4. To the negative 1, I get 2. Anything to the 0 power is 1. To the first power is 1/2. Squared is 1/4. And I'm starting to get smaller and smaller and smaller. So what that looks like is it's like an exponential function just reflected across the y-axis. So he starts big, comes down, goes through 0, 1, and then starts approaching the horizontal asymptote. Definitely want you guys to draw this picture. You don't have to do the table, but definitely draw the picture of this. Okay, so if we look at y equals 2 to the x, that's our classic, starts at our horizontal asymptote, builds, goes through 0, 1, 1, 2, it increases. If I write my function as y equals 2 to the negative x, so I'm replacing x with negative x, it reflects it across the y-axis, which is, we talked about that reflection in earlier chapters. And remember, having a negative for your exponent causes you to have the reciprocal and the positive exponent. So that is why that is true. You have to write that down. All right. So if we're going to graph 3 to the x and 1/3 to the x, these guys are going to be reflections of each other across the y-axis. So here's the 1/6 to the x, here's the 1/3 to the x. And they are reflections across the y-axis from what we had before. So here are the properties of exponential functions when our base is between 0 and 1. So when we have a decimal or a fraction that's between 0 and 1. The domain is the set of all real numbers, and the range is still the set of positive real numbers, so we're talking about above the x-axis. There are no x-intercepts, and the y-intercept is still 1. The x-axis, y equals 0, is still a horizontal asymptote, but this time it's as x approaches infinity. F of x equals a to the x from 0, as long as a is between 0 and 1. It's a decreasing function, and it is 1 to 1. The following still applies. It still contains the point 0, 1, 1 comma a, and negative 1 comma 1 over a. The graph is smooth and continuous with no corners or gaps. So essentially the same as the one previous, except for the horizontal asymptote. All right, so we use the same transformations as we have been since we started doing transformations. We're going to determine the domain and range and the horizontal asymptote. So if I look here, I have a reflection across the y-axis because I've replaced, if our parent function is f of x equals 2 to the x, then I've got a y-axis reflection, and I've got a shift of 3 down. So here's y equals 2x, sorry, 2 to the x. Reflecting it across the y-axis takes everything and takes our x values and changes the sign. And then we are going to shift it 3 units down. So this is our resulting function. The range, the domain, is there any restriction on our domain? Oh, where'd it go? Decided not. Okay, that's fine. So there is no restriction on our domain. It's still the set of all real numbers. And then our range is from -3, not included, to infinity. Because it was 0, but then we bumped it down 3 units, so now it's -3 to infinity. Why is -3 not included in our range? So -3 is our new, y equals -3 is our new horizontal asymptote. It was at y equals 0. And since it's an asymptote, we're never actually going to touch it. We're just going to get really close to it. That's why it's -3 is not included. All right. Our special number e. The number e is defined as 1 plus 1 over n to the n power as n gets larger and larger. We write that e equals the limit as n approaches infinity of 1 plus 1 over n to the n power. All right, and then you can test it out if you really want to. As you put larger and larger numbers in for n, you get closer and closer to the decimal approximation. E is a similar number to pi. So they're both irrational. And they both can go on forever. So when we have the function y equals e to the x, it's still an exponential function. It's still going to follow the same pattern as our other exponential function. The base is bigger than 1, so it's going to follow that type of function. All right, so the same rules apply. We use transformations, whether our base is e or our base is 2. For this, This is going to give us a horizontal shift 3 units to the right, and it's going to give us a reflection across the x-axis. So if we start out with our normal e function, goes through 0, 1, 1 comma 2.72, and 2 comma 7.39. We are going to reflect it across the x-axis, which just means we're going to take our y values and and change the signs. And then we're going to shift it 3 units to the right. And when we do that, we go, does that change my range or my the domain? Is there any restrictions on what I can input in for x? And know that we can still just put in all real numbers. And my range is going to be from 0 to negative infinity, not included. My horizontal asymptote is still at y equals 0. All right, now we're going to solve these things. This is exciting. This is what I love. So if I can get my exponential functions to have the same base, I can then ignore the base and have my exponents just equal to each other. So if a to the u equals a to the v, then u equals v. And we're going to start having to get creative on this. It's going to be amazing. For example, if I have 2 to the 3x minus 1 equals 32, I know that 32 is a special number. He is 2 to the 5th power. So if I can rewrite 32 as 2 to the 5th power, then I can just ignore the bases and solve. 3x minus 1 equals 5. So we add 1 to both sides, divide by 3, and we get x equals 2. If I have e to the 2x minus 1 times 1 over e to the 3x times e to the negative 4 to the, or negative x to the 4th power. Goodness gracious, let's simplify that out a little bit. So if I multiply my exponents together, negative x times 4 is negative 4x over 3x. And then I can, when I have division, I subtract my exponents. So this is going to be e to the negative 4x minus 3x is e to the negative 7x. And then I can ignore the e's and just go 2x minus 1 equals negative 7x. This is pretty intense algebra. Then I subtract 2x from both sides and divide by negative 9, and I get x equals 1/9. All right, exponential probability. Between 9 and 10 p.m., cars arrive at Burger King's drive-thru at the rate of 12 cars per hour, which is 0.2 cars per minute. The following formula from statistics can be used to determine the probability that a car will arrive within t minutes of 9 p.m. Determine that the probability of a car will arrive within 5 minutes of 9 p.m. That is before 9:05 p.m. So we are going to plug in 5 for our t value because we want to arrive within 5 minutes. And we're just going to plug this number into the calculator. I would like you to attempt to do this now. Make sure that you're getting out 0.63212, and I'll definitely stop and let you guys do that. All right, so let's do the same thing, but within 30 minutes. So we're going to plug in 30, and we have a 99.75% chance. What value does f approach as t becomes unbounded in the positive direction? So essentially, f gets closer and closer to 1, right? Or 100%, because eventually all the people are going to show up. As time passes, the probability that a car will arrive increases. The value of f, the value that f approaches can be found by letting t go to infinity. Since e is negative 0.2t, which is equal to 1 over e to the 0.2t. And as that approaches 0 as t approaches infinity, we conclude that f approaches 1 because of this. If this is 0, 1 minus 0 is going to be 1. So the algebraic, so f approaches 1 as t gets large. And that makes sense because that means it's 100% chance that your car arrived. All right. Properties of exponential functions, and that's the end of our lesson today.